Relativity, the idea that everything is relative, right? Relative to your perspective, your upbringing, your age, your place, and orientation in space and time. Except that plenty of things, in fact, perhaps most things, aren't relative. For example, George Washington was the first president of the United States. World War I happened before the movie Star Wars was made, this picture shows 3 apples, and so on. It is true that certain things are relative to one's perspective. Is the apple on your left or my right? Is 50 degrees Fahrenheit hot or cold? Is a car fast or slow? Big or small? And the fact that they're relative is precisely what makes these concepts less interesting to scientists. In physics and in most science, anything that changes if you change perspective can't be a fundamental property of the universe. Only things that are absolute are considered physical or real. And for a long time, physicists thought that distances in space and intervals of time were absolute fundamental properties in the universe. The special theory of relativity, first described by Albert Einstein, was merely a statement of the realization that we were wrong. Distances in space and time are actually relative. They change depending on how fast you're moving. But more importantly, Einstein also described several quantities related to space and time, which are absolute. The distance between 2 events in space-time, the energy momentum of an object, and of course, the speed of light. Special and general relativity are, at their core, not about what's relative. They're about what's real, irrespective of perspective. If everything were relative, then there could be no science, no laws, no justice, just opinion. Science exists because it turns out there are absolutes in the universe, truths which are the same regardless of your perspective. You might even say that science is simply about finding the truths that will still be true if you remove the scientist. So, goodbye.
Again, special relativity is a fundamental theory concerning space and time. Special relativity is special in that it deals with uniformly moving reference frames, ones that aren't accelerating. General relativity, which we'll discuss later, is general and deals also with accelerating systems. The general theory of relativity presents a new theory of gravity, one that, interestingly, corresponds to Newton's theory of gravity for less than enormous masses. You'll learn why Einstein postulated that the speed of light in free space is the same for all observers, regardless of any motion relative to the light source. If a light source moves toward you or moves away from you, you know what? You will always measure the same speed for light. Even if you're in a spaceship moving away from a light source at half the speed of light, you'll measure the speed of light from that source to be the same as if no motion were occurring. Why that is true involves the special relationship between space and time. After all, speed is a ratio of space and time. It just so happens that you can't change one without changing the other. The distance that light travels per amount of time taken is a constant, the same for all observers in all circumstances. So we find space and time melded together to make up what we call space-time. Quite remarkable. Einstein went further. He postulated that nature's laws are the same in all uniformly moving systems. If you perform an experiment in your basement, done correctly, the results would be the same if you performed the same experiment traveling at constant speed in a supersonic aircraft. Furthermore, no experiment can distinguish between uniform motion and rest. You've been in a bus and thought you were moving when you discovered that you're at rest and the bus next to you moves? This can be confusing. If it's done in space where there aren't any background clues, you wouldn't be able to tell who is moving. Are you moving or the other guy? A lot to think about. Einstein's ideas present a whole new way of looking at nature. The results of these ideas are far-reaching. Even the GPS systems we use every day have to take account of the effect of motion on time and of gravity on time. So let's learn more about special relativity.
When I was young, I was fascinated by elevators. When you went up, everything else seemed to go down. When you go down, the world goes up. When I got older, I got used to the notion that the world isn't really going up or down, but that the only one that was moving was me. Yet, it is somewhat a mistake to ignore what we see. The truth is that going forward, for example in a train, does not affect the Earth too much, but the Earth is moving relative to the people inside. That's the basis of relativity. Sound simple? Someone moving at relative speed to someone else would look to the other one as if he was moving in opposite direction and in the same speed, and that is as complicated as it gets. But something did not fit. You see, the knowledge gained during the last decades of the 19th century gave more than a hint to the possibility that light does not adhere to relativity. Everyone, moving fast or slow, seemed to be having essentially the same speed of light. It seems benign, but look at that. This craft travels at speeds close to the speed of light. What you just saw was two simultaneous lightning strikes at the forefront and back of the craft. Now, you can see the light from both events coming towards the person in the middle as he is moving towards the light from the front, and the light from the back have to chase him. So, he will see the lightning from the front first. So far so good. However, and pay close attention to this, relative to him, the light comes at the same speed and takes the same time to reach him from both directions. So for him, seeing the front lightning strikes before the one in the back means the front striked first. Something is very wrong. Or is it? The greatness of Einstein was that he managed to understand it is possible to reconcile relativity with a notion of unchanging speed of light. He did that by adding something to the theory of relativity. Time. Time, he said, is relative. Simultaneity is relative.
According to Maxwell, light was an electromagnetic wave that moved through empty space with a speed of 186,000 miles per second. But from the standpoint of relativity, the question naturally arises: relative to what? The equation seemed to say that light moved at 186,000 miles per second, relative to everything. This was a dilemma facing the physicists at the turn of the 20th century. If Maxwell was right, then light moves with a velocity of c, 186,000 miles per second, always. But if classical relativity was right, there is no absolute velocities, and the velocity of light should depend on who is doing the measuring and their motion relative to the source of the light. How could both be right? Either our understanding of motion or our understanding of electromagnetism and light were in jeopardy. The very foundation of physics was facing a crisis. A 26-year-old patent clerk named Albert Einstein would provide the way out of this crisis. Einstein accepted both of these seemingly contradictory notions and changed the course of science. He accepted the idea of relative motion but restated it as follows: any person moving at a constant velocity will observe the same laws of physics that a stationary person observes. And since the speed of light is part of the laws of physics, Einstein postulated that all observers will measure the same speed of light, regardless of their state of motion. But speed is just a measure of distance moved in a given time. And in order to agree on the speed of light, different observers might have to disagree about distance and time.
The bizarre consequences of special relativity arise from two postulates, two things which, once accepted, lead to Einstein's space-time. In this series of 5 episodes, we will introduce and build upon these postulates to derive the consequences of special relativity. So, are you ready? Okay then. Fasten your safety belt and prepare for takeoff. Imagine you're waiting on the runway and decide to take a nap. When you awake, all the window shades are drawn, and no one is in the cabin. So, can you determine without peeking out the window whether or not you're on the tarmac or flying in a straight line at a constant speed? You might think that dropping something would help, but it doesn't. Some people reason that if they drop something and it falls straight down, they aren't moving. But really, all this does is establish that they aren't accelerating. This is sometimes known as Galilean relativity, and it's why we don't perceive the Earth's rotation. For a sailor traveling at a constant speed in a straight line, a cannonball dropped from the crow's nest falls straight down. To a landlocked observer, however, both the ball and the ship are moving forward, and so the ball is seen to follow an arc. This means dropping something can't tell you if you're moving. It looks the same to you either way, as long as you're undergoing uniform motion. Now, if the plane was to suddenly speed up after you released the bag of peanuts, then it wouldn't land directly below your hand. However, this is what's special about special relativity. We are concerned only with things standing still or moving in straight lines at a constant speed, what we call uniform motion. This introduces the first postulate. There is no experiment you can perform to determine if you are standing still or moving in a straight line at a constant speed. Yes, you could have looked out the windows, but all you could have said for sure is that the ground and the earth were moving relative to each other. The plane could be the still one, with the earth rotating below. It's all a matter of perspective. It's all relative. All right then. Are we happy with the first postulate? The most one can say is that she is not speeding up, slowing down, or changing direction. She cannot say whether this is because she is standing still or moving at a constant speed in a straight line. It might help to consider that there is no absolute reference frame in the universe with which to compare one's motion. Remember, the Earth is hurtling around the Sun, and the Sun around the center of the Milky Way. The best we can say is, I'm moving relative to this or to that. Okay then, let's go to a parade. You're throwing candy to onlookers, and normally you throw candy at 5 miles an hour relative to yourself. The truck is trotting along at 2 miles an hour. So when you throw candy to people behind the truck, you are throwing opposite the truck's motion, and the candy reaches them traveling slower than it would if you were standing still relative to them. How much slower? Well, you subtract the truck's speed from that of your throw and find 3 miles an hour. When you throw the candy forward, it's moving with the truck, and so hits the spectators going 7 miles an hour, your pitching speed plus that of the truck. Got it? Good, because now things get weird. Light, it turns out, is special. It doesn't behave like candy, trucks, baseballs, or any material object for that matter. To see what I mean, let's wait for nightfall. Now imagine you're standing still next to a stationary truck. We can think of the light coming from the headlights as little particles or waves. Take your pick. What's important is that we measure how fast they're leaving the truck. This is like your pitching speed at the parade. When we do this, we find the light is leaving at 670 million miles an hour. Now, let's have the truck zoom towards us at 10 miles an hour and measure the speed of the light leaving the headlights. How fast do you think it's going? 670 million miles an hour plus 10? Well, that would be wrong. No matter what, we measure the speed of light to be 670 million miles an hour. It doesn't matter if the truck is moving at 600 million miles an hour. We don't add its speed to that of the light leaving the truck. That's the second postulate. The speed of light is the same for all observers undergoing uniform motion. That is, standing still or moving in a straight line at a constant speed. This is an empirical fact. Yes, the speed of light changes when it moves through glass or water, but we're not concerned with these complications. The speed of light in a vacuum is always 670 million miles an hour. It might seem odd, but experiments show this to be true. Now, if you can accept this and the first postulate, you're ready for relativity. They're all you need. Everything else just follows. So, keep an eye out for the following terms: space-time diagram, line of constant position, line of constant time, space-time event, and world line. We're used to documenting things with film, but let's make it even simpler. Say we replace film with a large roll of paper and attach a marker to those objects we find interesting. For now, this block on wheels and a road sign. All the while, our paper moves with a constant speed downward. This produces what physicists call a space-time diagram. By virtue of our setup, the vertical contains information about time and the horizontal about position. The lines traced by the markers are known as world lines because they document the history, the world, of their owners. To read our diagram, we employ the use of lines of constant position and time. A line of constant position represents one place. Any collection of events occurring on a line of constant position occur at the same place, just at different times. Similarly, a line of constant time represents one instant. Any collection of events occupying a line of constant time take place at the same time, but at different places. This diagram is simply a graph of time versus position. With our two types of constant lines, we can define any point in our diagram. Such a point represents a particular place at a particular time. Something we'll call a space-time event. A world line is nothing more than a record of these events for its owner. By working backwards from our intersection of constant lines, we can tell where and when something happened.